Okay, 7.1, modeling with differential equations. So this unit is all about differential equations. A differential equation is an equation that connects a function with its rate of change, so think derivative, okay, and is used to describe that change over time and space. So we have two types of differential equations when we're looking at modeling, so these application type problems, and one is directly proportional, which they'll just say proportional, and that is to say if A is proportional to B, then A is equal to K times B, where K is a constant. And then we have inversely proportional, and it says if A is inversely proportional to B, then we can say A is equal to K divided by B, or A is equal to K times 1 over B. Okay, again, where K is a constant. So in these examples, it says write a differential equation that describes each relationship. If necessary, use K as the constant of proportionality. So number 1 says the rate of change of y with respect to x is proportional to the product of t and the rate of change of w with respect to x. So we have several things happening here. We have the rate of change of y with respect to x. So that is dy dx. Then we have is, so that's equal to. And then we have proportional to the product of t. So proportion to the product of t. Proportional means our constant is being multiplied. So this is going to be k times t. And then it says, and the rate of change of w with respect to x. Okay, so we would write that as dw dx. And that would be our differential equation. Number 2 says the force F of a spring on a trampoline can be related to the distance d it is stretched. The rate of change of the quantity of F with respect to d is inversely proportional to the natural log of the distance d. Okay, so we have two things happening here. We have the rate of change of df dd is equal to inversely proportional. So we're dividing here. K divided by the natural log of d. Okay. Then it's going to give us some additional information. It says if the rate of change of F is 3 units per centimeter, then the spring has been stretched to 0.2 centimeters. What is the differential equation for this situation? So here it's actually giving us information to plug in for df dd and for d in order for us to simplify for k. So we have 3 is equal to k divided by the natural log of 0.2. And if we were to plug this in and solve for k, which we would have to use Desmos or a calculator, we would get k is approximately negative 4.828, which means our differential equation df dd is equal to negative 4.828 divided by the natural log of d. So sometimes they can give us additional information to solve for k, but since this is just us setting up the differential equation, it's not necessary for them to give us the k value. Okay, last one, number 3, says Mr. Burst is swimming in a straight line across a lake. His position from his starting point is given by P of t, where t is measured in the minutes since the start of his swim. During the first 30 seconds, Mr. Burt's acceleration is proportional to the cube root of time since the start of his swim. Write a differential equation that describes this relationship. So notice here it says P of t. Okay, so position function. But then it says acceleration. Well, we need to know that acceleration is the second derivative of the position function. And if we were to write this in terms of dp dt, this would be d squared p over dt squared, representing that second derivative. So that is our acceleration. Okay, so it says acceleration is, so that's equal to, then it says proportional to the cube root of time. So proportional means multiply, so K times the cube root, so cube root of time. Okay, and that is going to be our differential equation.